traveling sound waves. Let's look in some detail at the displacement and the pressure variations that we associate with a sinusoidal sound wave passing through air. This is a very long tube with air transmit from right to left. Okay. Consider a thin element of air of thickness delta x, located at a position x along the tube. Not this one. The location is x, the thickness delta x. Okay. As the wave passes through x, the element of air oscillates left and right in simple harmonic motion about its equilibrium position. Okay. Now we enlarge it. This piece is here. Okay, delta x. When the wave passes, okay, it will vibrate around its equilibrium position with amplitude Sm. Okay, again Sm. This Sm is much smaller than wavelength. Okay, and the pressure change because the violation is much smaller than the press in the tube. Okay. Thus, the oscillations of each air element due to the passing sound wave are like those of a string element due to a transverse wave, except that the air element oscillates longitudinally rather than transversely. To describe the displacement Sxt of an element of air from its equilibrium position, we can use either a sine function or a cosine function. In this chapter, we use a cosine function. S equals Sm cosine kx minus omega t. Here, Sm is the displacement amplitude. That is, the maximum displacement of the air element to either side of its equilibrium position. The angular wave number k, angular frequency omega, frequency f, wavelength lambda, speed v, and period k for a sound longitudinal wave are defined and interrelated exactly as for transverse wave, except that the lambda is now displacement again along the direction of the travel, in which the pattern of compression and expressions due to the wave begins to repeat itself. And this is the one that repeat. This is the one. This is the one. This is lambda. Okay. We assume Sm is much less than lambda, and we will prove it. Now let's look at this one. This is a slide of air. This is a cross area. This is the thickness delta x. Their vibration are different. So their displacement, this and this are different. This is we call it Sx. This is called x plus delta x, or we write Sx plus minus delta x, delta s. Okay? Then after a while, this v equal to a delta t. This is s. And after a while, the red volume become the blue volume, because they are velocity different, so they are different. Okay? With the delta v as before. The delta v, the blue volume minus the red volume, this is part is very common. So that delta v equal to this volume called S x plus s times a minus this one Sx plus a. Okay, this is a displacement. Okay, and b we know equal to rho v squared. Then we see delta p equal to minus b v delta v over v. This is we learn stretch equal to modulus by the strain. Okay, So delta P equal to minus B rho V squared. This is delta V, A delta S. V is A delta X. And A cancel out. Delta X, delta S, delta X, we can write it rho S, rho X. And rho X, we do the derivative. Rho X, cosine because minus sign, and you have a K outside. So you get minus rho V K. This one. You get minus sign, minus might get a sign. Sm, you have a K out. So you get rho V squared K Sm sine. This is a sine. This we call it delta Pm, where delta Pm equal to rho V squared K Sm is the maximum pressure variation. It is normally very much less than the pressure P that it prevails when there is no wave. Now we look at this one. Okay. Recall that we can produce such a wave, but sinusoidally moving a piston at the left end of the tube. Okay, the piston's rightward motion moves the element of air next to it, and the compressed air, the passing leftward motion allow the element of air to move back to the left and the pressure to decrease. As each element of air pushes on the next element in turn, the right-left motion of the air and the change of its pressure traveling along the tube are sound waves. This is displacement of air element. This is the pressure variations. They are both sinusoidal, okay, cosine sine. Okay, the delta P equal to rho V squared KSM. But when it's cosine, when it's sine, they have phase different half pi or 90 degree. Okay. When a sound passes through air, both the pressure variation and the displacement of a slice of air are sinusoidal, so cosine sine. But two waves are half pi radius or 90 degree out of phase. The pressure varies between zero, this is zero, this is minimum, maximum. Okay, when the displacement is a maximum. This is a displacement, this is a pressure variation. They have 90 degree different. Okay, this maximum, you move 90 degree. There is a phase difference, 90 degree, between delta P and S, delta P and Sm. Sm is much smaller than the wavelength lambda, and delta P is much less than the P. Experimentally, it is usually easier to measure the pressure variation than measure the displacement. Sample. The maximum pressure amplitude delta Pm that the human ear can tolerate in loud sounds is about 28 Pascal, which is very much less than the normal air pressure of about 1 atmosphere, 1 to the 5th Pascal. What is the displacement amplitude Sm for such a sound in air of density rho 1.21 kilogram per cubic meter at a frequency 1000 Hertz and a speed of 343 meters per second. This is a very simple one, just plus the number, okay? We know delta P equal to rho V omega sine Fc. What do we find? We know this one. We will find Sm. So Sm equal to delta P over rho V omega. Then we put that. Delta P is 28, V is 343, rho is 1.2 kilogram, and omega is thousandths per 2 pi. You get 11 micrometer. How large it is? Micrometer, very small. I tell you, this is about our hair, diameter of our hair is about 100 micrometer. So this is very tiny. The largest sun, okay? And this Sn is much less than lambda. When lambda, the frequency 1000, okay, then there's a V over frequency equal to lambda, 0.34 meter. It's much, much larger than this one, okay? Now we look at the minimum situation. The minimum situation, that it probably is 2.8 times 10 to the 5th Pascal, about a million different smaller than this one. And in this case, we calculate S minimum is about 0.1 angstrom, about 11 picometer, very, very. So our ear is a very sensitive instrument. Interference. Figure shows 2-point source S1 and S2 that emits sound wave of wavelength lambda in phase. That is, the emerging waves reach their maximum displacement value simultaneously. Okay? Suppose also that the sound waves passing through some common point P while traveling in approximately the same direction. If they have traveled along paths with identical length, L1 equal to L2, to reach the point P, they will be in phase there. However, if they have traveled along paths with different lengths, as in the figure, L2, L1 are different, they may not be in phase. They can be in phase too, but they not be in phase. Their phase difference phi at point P depends on path length difference. Delta L equals L2 minus S1. Since the phase difference phi of 2 pi radius corresponds to one wavelength lambda, thus we can write the proportion phi delta V, 2 pi lambda, and we can calculate the phi phase difference from delta L. So phi equal to 2 pi over lambda delta L, or 2 pi over delta over 8. Okay. From delta L, we can find the phase difference between the two waves. When two waves travel along different paths, the path length difference delta L can alter their phase difference phi. They undergo interference. Fully constructive interference means the phi equal to 2 pi multiplied by an integral m. M can be 0, 1, 2, 3, and so on. Or delta L can be lambda multiplied by times. M can be 0, 1, 2. For fully destructive interference, the phi is this one plus half 2 pi minus the same. M can be 0, 1, 2. Or delta L equal to m lambda plus half lambda or minus half lambda, where m can be 1c. Okay.
Two speakers at the ends of this boom arm will be used to demonstrate interference of sound waves. Both speakers are driven in phase by an audio oscillator. A microphone placed in front of the boom arm will pick up the combined sound signal from the two speakers for you to hear. Here's how that sound varies as we rotate the boom arm. Notice the intensity pattern of the sound. There are points of high intensity and low intensity at regular intervals. If we double the frequency of the sound, how will that affect the intensity pattern? The points of high and low sound intensity are now closer together.
Sample. In figure, 2 point sources S1 and S2, which are in phase and separate by distance d equal to 0.5 lambda, emitted identical sound waves of wavelength lambda. Question A. What is the path length difference of the wavelengths from S1 and S2 at point P1, which lies on the perpendicular bisect of distance d, at a distance greater than d from the sources? What type of interference occurs at P1? We know the delta L, L1 and L2 at point P1 is the same. So delta L equal to 0. That means the sound interference, they are fully constructed in phase. What are the path length difference and types of the interference at point P2? And the P2 is on the line, extend the line. We know the distance L1 and L2 is always d, and the d is 1.5 lambda. Okay? So delta L equal to 1.5, that means the sound here is always fully destructive. Okay? Question C. Figure B shows a circle with a radius much greater than d, center on the midpoint between the source S1 and S2. What is the number of point n around its circle at which the interference is fully constructed? That is, how many points on the circle which is fully constructed? Now we look at this one. As we calculate, these two are always fully constructed. These two, the phase difference or the path difference 1.5 lambda, okay? 1.5 lambda. So this is 0, this is 1.5. In the between, you have 1 lambda difference. In other words, this is a 1 lambda force. At this point, is fully instructive because 1 lambda difference equal to 2 pi difference is fully instructive. Okay, so all this one we want to find it 1, 2, 3, 4, 5, 6. The number is 2 plus 4, 6 fully constructive.